Hello and welcome to our session number 17. This should be the last session when we talk about metal semiconductor or Schottky barrier junctions. And next time, hopefully, we'll be going on to PN junctions, a few sections on the PN junction, and then we'll be dropping into the bipolar junction transistor. So today we're going to be talking a little bit about depletion capacitance. Some of it is a review. We introduced it, I think, 2 sessions ago. Then I want to go back and talk a little bit about the current density in Schottky barrier junctions and the fact that the current in these particular devices are majority carriers, and that is going to be quite a difference from the PN junction where the carriers are minority carriers, and we'll have to talk about the minority carrier diffusion equation. And then finally, we'll look at some examples and worked problems. We'll begin with a very lively rendition of the Liszt Hungarian Rhapsody number 2, I believe. And we'll see you in about 4 minutes. Okay, so this is a rough outline of some of the topics we'll be covering today in session 17. We are going to review the depletion region capacitance. Hopefully I'll say something a little bit different, which will be not a complete repeat of what we said the last time. And then we'll look at majority carriers in Schottky barrier junctions, and we'll realize that Schottky barrier junctions are majority carrier devices, which means that drift current is applicable and we don't have to worry about the minority carrier diffusion equation, which we will have to worry about quite a bit in PN junctions. Or not worry about, we'll deal with. And then we'll spend the bulk of our time doing some examples and problems. Okay, so we'll start with the depletion region capacitance, which we looked at in our last session. Charge is equal to capacitance times voltage. It's a linear relationship if C is constant only depending on the structure. Well, that's not the case for depletion capacitance, because the distance between the quote-unquote electrodes, the metal and the quasi-neutral region, depends on the applied bias. And that is really a big deal. And that characterizes this equation. And it really says that this is more or less like what we call a varactor diode. C depends upon V. So I can't use this exactly as it sits. For any structure, a parallel plate capacitor, the capacitance is equal to the permittivity multiplied by the cross-sectional area that's going into the paper here, divided by the width. And the width for an applied bias is equal to an expression which we derive in Chapter 8. We talked about it quite a bit in sessions 15. And it's sitting right here. We stick in W into this equation, and since W is square root, we'll simply take the square and we get the capacitance squared, and here it sits in equation 9.4. This is in equilibrium. There's no VA here. We're going to put in the VA later on. Notice that we have farads per square centimeter. Now, really, this should be farads per square centimeter all squared, but so I'm being a little bit sloppy here. The important point is that the capacitance in a depletion region capacitance is not the normal capacitance, permittivity area over W, but we shift out the area, so it becomes what we call an areal capacitance, and it's measured in farads per square meters, per square centimeters in our case. So we want to get this as a linear function of the applied bias, so what we do is we flip it. So 1 over c squared, we just flip this on its edge. Numerator becomes denominator, denominator becomes the numerator, and this is the full expression, equation 9.42. So we have 1 over c squared as a linear function of the applied bias VA. Two things we can get from this: the slope, which is sitting in the denominator, permittivity multiplied by the charge density, and the point where the VBI becomes equal to VA. We're going to measure VA, but we'd like to determine VBI, and this allows us to do that. So the doping density is determined by the slope, and VBI is found where the intercept, where VA, which we measure, is equal to VBI, and that's right here. Notice that the slope is positive. Everything here is positive. We have, for reverse bias, that is in this region here, we have large positive VAs, and for the interface right here, this is the equilibrium point, and this goes into forward bias, becomes very difficult to measure. Capacitance becomes very large. 1 over the capacitance becomes very small, and we just basically get a couple of points over here. We extend the line down until we get 1 over c squared is equal to 0, and that is the band bending. Okay, so all of that is for N-type, and if we go to P-type, using the basic principle, everything we say for N-type, it just flips on its edge for P-type. So if N-type looks like this, we can expect the slope would be negative and the intercept would be positive, and that's exactly what we find here. The slope still determines the doping density, and the intercept still determines the amount of band bending, but everything is flipped for P-type. Now the effect of doping, this again is for P-type. Low doping concentration corresponds to a high slope, and we can see that from the basic equation. As n goes down, the slope of this curve, 1 over c squared, goes up. That's this curve here. And for high doping, n goes up. Then 1 over c squared goes down, and the slope becomes much more shallow. And of course, also the VBIs can change also for high doping and for low doping, and indeed they will. So now I want to say a word about majority and minority carriers in PN junctions and Schottky barriers. Schottky barriers are majority devices, and the reason is, for example, in an N-type silicon rectifying Schottky barrier, the thing that moves, the stuff that moves, the charges that move are electrons. Electrons are majority carriers in N-type silicon. So we have drift current rather than diffusion current, and the operative expression is the one we developed way back in, I think, the first or second session. The current density is equal to the number of charges per cubic centimeter, that's n, electronic charge E, multiplied by the velocity, and the velocity of the charges is equal to the mobility times the electric field. So the thing that determines the current are n. We use all the machinery that we developed for equilibrium devices, Boltzmann statistics, and all of those equations, the laws of mass action, things like that, will give us this guy here, and that's a very important determinant of the current density, J. E, the electric field, is the external electric field, and that we're going to basically massage into the amount of energy that we have to overcome the barrier. And if we look at this picture here, we see that there are actually two fields. There's an internal electric field, and this is in N-type because we know that bands bend up. So we have positive ions in the depletion region, a negative surface charge density at the metal surface. So the electric field points from right to left. It is negative. In forward bias, where we have relatively large currents, we have an electric field which opposes the internal electric field. And as this electric field, the external electric field, goes up, then this band barrier, or the band gap, or the band bending goes down. So that's really quite a big deal. The other thing is that the internal electric field forces electrons to go from left to right, which is a negative current because it's opposition to the internal electric field, which is in the direction that a hole would move. Electron would move in the opposite direction. The external electric field, holes move from left to right, or electrons move from right to left. So this external electric field pushes electrons around a circuit in a counterclockwise manner. Counterclockwise. Okay. So I just mentioned that the full derivation is found in section 9.7. It's a little bit long to go through it, but I believe it's reasonably straightforward, so I hope you'll be able to follow it without too much difficulty. Again, as we mentioned in our last session, it's composed of two parts. This is the forward bias part, where the current increases exponentially with VA. This is the reverse bias part, where the current is approximately constant because phi Bn is approximately constant. The current is a rather intimate and strong, has a strong variation with temperature. So all this at room temperature, we get reasonably large currents in forward bias. We get very small currents in negative reverse bias. We'll see, because the barriers in forward bias, in Schottky barriers, tend to be significantly smaller because there is only one barrier. This is the barrier right here, PBI. In PN junctions, we'll have another barrier. We'll have a barrier on the N side, and we'll also have a barrier on the P side. So for Schottky barriers, we can get larger currents, so that's a good thing, and we get fast turn-on times. We'll see why, because drift current tends to be fast, diffusion current tends to be a little bit slower, so Schottky barriers are good at high frequencies. However, there's always a downside. Nothing's perfect in life. The problem in Schottky barriers is this guy doesn't change, so we get relatively high reverse currents, whereas in PN junctions, in reverse currents, I can make the barriers extremely large, so the currents in reverse bias for PN junctions are smaller than they are for Schottky barriers. And I probably should make one more comment about the capacitance voltage diagrams, or CV diagrams. We will see them again and again and again in all of our structures. They all have the same form. They all have the same basic idea that the slope is determined by the doping density and the intercept determines the band bending. So we'll see that again. So I should say, not unfortunately, but it's something that once we learn it for Schottkys, it'll be easier to learn it for PN junctions and BJTs and MOSs and all the other stuff that we'll be looking at. Okay, so now let's look at some examples. This is example number 1, and we're asked a bunch of questions. First, we're given, this is the numbers we're given. We're given that it has an applied bias of 2.3 volts, and we're going to be asked, what does that mean? That's a pretty big number. So we'll see what that number means, its magnitude. We're given that the constant barrier, the VBP in this case, the constant barrier is 0.5 volts. We're going to be asked to find the band bending, the variable barrier, VBP, and we're given that the Fermi level is 0.25 eV above the valence band. Is the structure rectifying or non-rectifying? The giveaway here is the bands are bending, and they're bending pretty hard. So clearly this is rectifying. I should mention before we continue, this is definitely not, and that's why I should probably should put this in font 30 or something, definitely not to scale, because 0.5 eV is the distance from here to here, and the distance from the applied bias is about 5 times that, so definitely not to scale. Is the device operating in equilibrium, forward or reverse bias? It's obviously not in equilibrium. It's either forward bias or reverse bias. We mentioned in the CV diagrams that or the current in a Schottky barriers, forward biases for Schottkys and for p-n junctions tend to be 0.2, 0.3, 0.4 volts. For Schottky barriers, a little bit less because you only have one barrier. 0.2 volts would be relatively typical. For reverse bias, we can go to extremely large values. So this is a pretty large value. It's a really large value. So clearly this is in reverse bias. Part B asks us to calculate the doping density. The doping density we're going to get from the position of the Fermi level, referenced either to the valence band or to the intrinsic. The intrinsic is up here. If it's 0.25 eV above the valence band, it's about 0.3 electron volts below intrinsic, and we've already seen that 0.3 volts below intrinsic corresponds to 10 to the 15th. If it was N-type doping, 0.3 volts above intrinsic would correspond also to a doping density of 10 to the 15th donors. Here is 10 to the 15th per cubic centimeters acceptors. And this value is independent of everything, basically. It only depends on the interior or the quasi-neutral region, and that's what determines the doping density. Okay, good. To calculate the Schottky barrier, we use an expression that we derived in section, I believe session 15, or it's also in the text, chapter 8. The constant barrier voltage we're given is 0.5 volts here, and that is equal to the affinity of silicon, which is 4.05 eV. The band gap is 1.15, and now we're asked to find the metal work function, so we just solve for phi sub n, and we find 4.65. We mentioned before this 4.6 is a rather interesting number, but suffice to say that 4.65, which corresponds, we look it up, it corresponds to metal of nickel. Nickel and gold having the high metal work functions. Okay, so now we know we can calculate phi bi. This is another expression which we derived, I think, explicitly in session 15 or 16, I forget which one. It's relatively straightforward. So we know that the phi BP is 0.5, and we know that the difference between the Fermi level and the valence band is 0.25. So we find that the band bending is 0.25 at equilibrium. We don't have an equilibrium situation here. Without this voltage, the band bending would be significantly less, and would only be 0.25 electron volts. Okay, part C. Gosh, what is part C? Yeah, okay. I'll calculate the depletion width. All right, that doesn't sound too bad. We have everything we need. Just write down the expression. The only question is, what sign do we use? What sign do we use for VA? What sign do plus or minus? We don't have to worry about any of that. We just use common sense. We know that for reverse bias, W increases, so it's going to be a positive number here. We don't kick out the minus, we just use the positive, and we assume that VA is also positive, and it adds to VBI. So we have VA of 2.3, we found VBI is something or other 0.25, so we add them together. So the number in parentheses here is 2.55. The permittivity of silicon is 10 to the minus 12th. The doping density is 10 to the 15th. Put all that stuff in, and we get 1.8 microns. Pretty large number. The reason that it is large consists of two factors. One is the light doping. 10 to the 15th is light doping. The lighter the doping, the more spread out the ions are in the depletion region, and the larger the depletion region. But the main thing is that the reverse bias is huge, 2.3 volts, and that's what gives us a relatively large depletion width. You'll notice here again, as the doping density goes up, the depletion region width goes down, and all of that hopefully makes sense. Okay, what's part D? Part D is, okay, if an electron-hole pair were to be created in the depletion region, show the directions of electron and hole motions. Okay, that's pretty straightforward. We notice that here the electric field, the internal electric field, is in opposition to the external electric field, and we show that right here. If we're talking about the inside of the material, we're talking about, I should have actually perhaps mentioned here, this is the internal electric field. The internal electric field points from left to right, and the reason is that we have negative ions in the depletion region, negative arsenic or boron ions, which means that the electric field points in the positive direction. Again, this is the internal electric field, which means that holes would go in the direction of that electric field, and electrons would be pushed opposite. So holes go from left to right, positive. It's a positive current. Electrons go from right to left, which is also a positive current. Okay, so for example 2, we go back to our original picture. Somewhere's here. There it is, right here. And we're asked 3 things. Determine the maximum electric field with no applied voltage, in other words, at equilibrium. The maximum electric field with the given applied voltage, reverse applied voltage of 2.3 volts, and the maximum electric field with applied forward bias of 0.2 volts. Now you notice the differences in the magnitude. Forward bias is very small. There's only one barrier, and it don't take much to overcome that barrier. So 0.2 would be typical, 0.3 would be typical, whereas reverse bias, we can put it basically as much as I want. Unfortunately, the current does not decrease as I apply larger and larger reverse biases, because the barrier is approximately constant, independent of reverse bias. So that's a problem with Schottky barriers. Okay, the other thing, before we start here, the maximum electric field will always occur at the metallurgical junction, or the interface between the metal and the silicon. So the position is not a problem, it's just the magnitude, and the electric field will vary linearly with voltage. The definition of electric field is it's equal to volts per centimeter. So E is equal to the first derivative of the voltage with respect to position. And oh, that's what I say. Here the electric field is a linear variation with charge, with X, because the charge density is constant. Okay, good. And the field is 0 at the depletion region edge. That's right here. The field is 0 in the quasi-neutral region. The edge of the depletion region is the point right there. And the maximum value, as we said, occurs right at the metallurgical junction. That also will be true for p-n junctions. I'm sort of trying to, through the back door, introduce a little bit of the p-n junction, because that will be our next topic. Okay, so this should actually be P2.1. It's a triangle, and the area under the triangle is going to be equal to the applied voltage. So that's a big deal. Okay, the area of a triangle is equal to 1/2 the height times the base. So once we find E max, we can find the area and we can find VBI under different conditions. Okay. So we'll start with equilibrium, where VBI is equal to 0.25 volts. We found that way back from example 1, that the barrier height is 0.25 electron volts if we're using phi. If we're using it in voltage, it's 0.25 volts. And we put all that into our equation. Again, the permittivity of silicon, the barrier height, and the doping density and charging. And we find that the depletion region is 0.56 microns, not 1.8 microns like we found way back up here. That's because of the very high reverse bias. But if we have an equilibrium condition, it is quite a bit smaller. And now we can find E max simply by using the area of a triangle. VBI is 0.25 times 2 is 0.5 divided by W. We find that the E max, the electric field at the metallurgical junction, is 9 times 10 to the 3rd volts per centimeter. So then we ask the question, should we expect a larger E max for reverse bias or smaller than equilibrium? Well, there's two things. They seem to be working against one another. The VBI for reverse bias is going to go up by quite a bit, but the W is also going to go up. So which one wins? Well, we'll see. We would expect the E max for reverse bias to be larger. In fact, we can kind of deduce that from the opposite. In forward bias, we would expect the electric field to go away completely if we have enough forward bias to completely overcome the barrier. So we would expect that reverse bias, the opposite occurs. So for reverse bias, we found the band banding is 2.55 and the W is 1.8. So we get a grand total of 2.8 times 10 to the 4th volts per centimeter. And that's quite a bit large. This actually should be twice this, by the way. It should be 2 times 2.55. Now let's look at a forward bias of 0.2 volts. And if we put that into our original expressions back in example 1, we find the band bending is only 0.025 volts, extremely small. Even though the forward bias is small, the band bending goes down quite a bit. And the depletion region is now 0.25 microns. So at equilibrium, it is 0.56, and forward bias, it actually goes down. Since it actually goes down, it goes down. We know it goes down, but it actually is less than half of that. So we put all those things in and we find a relatively small Emax of 4 times 10 to the 3rd as compared to the equilibrium of 8.9. So it's quite a bit smaller. And if we look at the plot of electric field, this is for P-type silicon, we find it has a negative slope but a positive value. It's positive value because in the depletion region, where's the depletion region? Oh my goodness, it must be something. There it is. In the depletion region, we have negative ions. So if we have negative ions, the internal electric field is positive, and that's why we have a positive electric field here, but the slope is negative. The electric field in the quasi-neutral region, which is here, is 0. At equilibrium, we have the middle line, and reverse bias, we have higher electric fields, and forward bias, we have smaller electric fields, but the slopes are the same. Why is the slope the same? Well, we saw that from the CV diagram. Also, the slope depends only on the doping density, and the doping density does not depend on the bias. So if we look at N-type silicon rather than P-type, we get exactly the reverse. The electric fields are non-negative because in the depletion region, we have positive ions, and at the surface metallurgical junction we have a negative charge density, so the electric field points from right to left, which is in the negative direction, and that is why we have negative electric fields, but we have a positive slope, and the slope is independent of the applied bias. Okay, so let's take a look at one more problem. This is chapter 10, which is the chapter of work problems. This is the first one. This is similar, but has some little twist to it. The problem explores some basic concepts in the Schottky barrier junction. We consider an aluminum metal. Now, aluminum metal, notice that the work function is quite a bit less than for nickel, 4.1 versus 4.65. That's more typical of most of the metals that we encounter. The two kind of outliners are nickel and gold. And the silicon work function is 4.3. 4.3, I would say, just off the top of my head, it's probably N-type. And they want to determine the silicon type and the doping. Is the structure rectifying or non-rectifying? Let's try to answer that question first, because we know that in a rectifying junction, the silicon work function must be less than the metal work function. It means that the silicon Fermi level is higher up, so that electrons can flow from the silicon into the metal. In this case, it's the opposite. The metal work function is actually smaller, so electrons will flow from the metal into the silicon. So I would say that the structure is non-rectifying. It's one of those unfortunate cases where we really don't have much of a device at all, which of course leads us into part B. If we just had this, then we wouldn't be much of a problem. Now, let the silicon work function be 4.9. That's big. That is bigger than phi sub m, and I would think, well, maybe we've got a rectifying guy in this case. With this new value, or the silicon work function, is the structure rectifying or non-rectifying? I would say probably rectifying. What is the silicon type? I would say, because of this large work function, probably P-type. And what is the doping density? And we'll see that those two things, the doping density has to be determined analytically. If you found that one of the structures is indeed rectifying, and of course, being a problem, you're always going to find that one of them is rectifying, and otherwise it wouldn't be much of a problem. Determine the charge density in the depletion region and the fixed barrier height, phi, and the built-in voltage, VBI. I shouldn't really be built-in voltage. The band bending VBI, and the maximum value of electric field. Okay, so it may seem strange that given only the work functions, we should be able to determine the doping density. Well, there is one piece of missing information which probably should have been supplied in the problem, or if it was an exam, it certainly would be supplied in a kind of a cheat sheet of constants. The affinity of silicon is 4.05. Nobody would remember. I certainly don't remember that. Nobody remembers that. So you have to know that the electron affinity of silicon is 4.05. So then we can have partial energy band diagram here showing the free electron level, affinity, and the work function. So to find silicon type, we need to know the position of the Fermi level. and we either need to know that in reference to the conduction band or to the intrinsic, because the intrinsic minus, I should say the conduction band edge minus intrinsic is 1/2 the band gap, or 0.55 or 0.56 EV. So we see that EC minus EF in this particular case is 0.25. So since EF is above intrinsic, this is in fact N-type, and it is N-type by 0.3 volts, 0.3 E volts, 0.3 electron volts above EI, so the doping density is 10 to the 15th. So is it rectifying or non-rectifying? We kind of answered that before, and it is not rectifying. It is the non-rectifying type. So in part B, we increase the metal work function from 4.1 to 4.9, and we suspect that that's a huge value. So we suspect that it's probably P-type, and indeed that will be the case. And we use this basic relationship for P-type silicon, and we know the work function, we know the affinity, so we find that the Fermi level is 0.85 eV below EC, and if I subtract 1/2 the doping, the band gap, I find it's about 0.3 eV below EI, and that also gives us a doping density of 10 to the 15th. So we went from two conditions, one where we had a small silicon work function, 4.1, to part B, where we have a large silicon work function of 4.9. They have the same doping density, except the first one with a small silicon work function is N-type, and the second one with the large silicon work function is P-type. Okay, now part C. Where is part C? Part C someplace. Part C. Okay, if you found that one of the structures is indeed rectifying, as indeed we did find, then we want to determine the charge density in the depletion region and the fixed barrier and the amount of band bending and the maximum value of the electric field. Okay, let's see if we can do that. The fixed boundary is given by this expression here, which again we derived in session, I believe it's session 15. We know the affinity is 4.05. We know the band gap is 1.1, 1.2, doesn't matter. One of those anyway. And for the metal work function, it's still aluminum. It's 4.1. So we found that the fixed bias is now 1.15 eV. So that is a really big number. Remember that the band bending we'll find anywhere from 0.3, 0.4, 0.5. In forward bias, it basically goes away. It's very small, 0.1, 0.2. For this particular case, in this P-type, the fixed barrier is 1.15. That's higher than generally we would ordinarily see it. It looks like a pretty big barrier, so we should get very small reverse currents, but it's not as small as the reverse barriers in PN junctions. Okay, electric field points to the right. In P-type, the bands bend down. The electric field always points to the right, so its electric field is positive. It has a negative slope, but it is positive, and that's shown here. Because for part B, we have this high silicon work function, and therefore it is P-type. Okay, so to find VBI, which now we got the units right, we multiply by charge, we can find phi BI, so because phi BI is just equal to the difference in the work functions between the metal and the silicon. In this case, The metal work function is 4.1. The silicon work function is 4.9. So the difference, absolute value, is 0.8 eV. So that's the barrier height for holes from silicon to metal, and is less than, and is almost, well, I should say almost, it always is less than the fixed barrier height from flow from metal to silicon. So we can find the depletion region using that VBI of 0.8. Again, everything else is standard, and we find the depletion region is about a micron. That is quite typical. I say it's relatively large because the doping is low, but it's not that, it's not nearly as large as we found in the previous example of 1.8 microns. So it's fairly decent value. Find the electric field. We know W, we know VBI, so we put all that stuff in, and we find 2, there's 0.8, and the depletion region is 1 micron, which is 10 to the minus 4th centimeters, so we find 1.6 times 10 to the 4th volts per centimeter. I would say it's not relatively low value. It's a typical value. Okay, so that pretty much ends our session for today. It was hopefully not too traumatic. We covered a lot of ground, but now we go on to PN junctions. So to end our session, I'd like to play a clip from this movie, Scent of a Woman. Al Pacino plays a blind colonel, army colonel, and he befriends a student at an exclusive prep school in New England. And this particular prep student, Charlie, is a student who was admitted on a scholarship. He's from a poor family. And Charlie and his friend George witness a prank played on the headmaster, Mr. Trask, a rather nasty trick that was played on him by 3 students. And both of them saw it, and neither of them is willing to come forward and be a snitch. So Al Pacino is defending Charlie in this scene, and it's got some incredibly powerful moments. So we'll see you next time.
He's the only party to this incident who is still worthy of calling himself a bared man. I'm going to recommend to the disciplinary committee that you be expelled. Mr. Sims, you are a cover-up artist and you are a liar.
But not a snitch.
Excuse me?
No, I don't think I will.
Mr. Slade.
This is such a crock of shit.
Please watch your language, Mr. Slade. You are in the Baird School, not a barracks. Mr. Sims, I will give you one final opportunity to speak on.
Mr. Sims doesn't want it. He doesn't need to be labeled still worthy of being a bared man. What the hell is that? What is your motto here? Boys, inform on your classmates, save your hide. Anything short of that, we're gonna burn you at the stake? Well, gentlemen, when the shit hits the fan, some guys run and some guys stay. Here's Charlie facing the fire, and there's George hiding in Big Daddy's pocket. And what are you doing? You're gonna reward George and destroy Charlie.
Are you finished, Mr. Slade?
No, I'm just getting warmed up. I don't know who went to this place. William Howard Taft, William Jennings Bryan, William Tell, whoever. Their spirit is dead, if they ever had one. It's gone. You're building a rat ship here. A vessel for seagoing snitches. And if you think you're preparing these minnows for manhood, you better think again. Because I say you are killing the very spirit this institution proclaims it instills. What a sham. What kind of a show are you guys putting on here today? I mean, the only class in this act is sitting next to me, and I'm here to tell you, this boy's soul is intact. It's non-negotiable. You know how I know? Someone here, and I'm not gonna say who, offered to buy it. Only Charlie here wasn't selling.
Sir, you're out of order.
Out of order? I show you out of order. You don't know what out of order is, Mr. Trask. I'd show you, but I'm too old. I'm too tired. I'm too fucking blind. If I were the man I was 5 years ago, I'd take a flamethrower to this place. Out of order. Who the hell do you think you're talking to? I've been around, you know. There was a time I could see, and I have seen boys like these, younger than these, their arms torn out, their legs ripped off. But there is nothing like the sight of an amputated spirit. There is no prosthetic for that. You think you're merely sending this splendid foot soldier back home to Argonne with his tail between his legs, but I say you are executing his soul. And why? Because he's not a bad man. Bad men. You hurt this boy, you're gonna be bad bums. The lot of you. And Harry, Jimmy, Trent, wherever you are out there, fuck you too.
Stand down, Mr. Slade.
I'm not finished. As I came in here, I heard those words. Cradle of leadership. Well, when the bow breaks, the cradle will fall. And it has fallen here. It has fallen. Makers of men. Creators of leaders. Be careful what kind of leaders you're producing here. I don't know if Charlie's silence here today is right or wrong. I'm not a judge or jury, but I can tell you this. He won't sell anybody out to buy his future. And that, my friends, is called integrity. That's called courage. Now that's the stuff leaders should be made of. Now I have come to the crossroads in my life. I always knew what the right path was. Without exception, I knew. But I never took it. You know why? It was too damn hard. Now here's Charlie. He's come to the crossroads. He has chosen a path. It's the right path. It's a path made of principle that leads to character. Let him continue on his journey. You hold this boy's future in your hands, committee. It's a valuable future. Believe me, don't destroy it, protect it. Embrace it. It's gonna make you proud one day, I promise you.